Good morning, everyone. My name is Victor Latotsky. I'm a volunteer with the CSPC Program Committee. I'm happy to introduce this plenary session on Canadian research facilities at the forefront of scientific breakthroughs, the long-term benefits of supporting fundamental research. Before we begin, there's just a couple of housekeeping items. The CSPC does offer simultaneous translation and closed captioning this year. Subtitles and closed captions are available in both official languages using the CSPC program app that you can access by scanning the QR code on the banners at the side or by downloading them from the Apple App Store or Google Play. Please tweet about your experience using @SciencePolicy or #CSPC2024. And finally, please remember to fill out the evaluation survey for the session using the CSPC 2024 program app. Thank you, and thank you for your attendance.
Is this on? Okay. Okay, bonjour. Good morning. I'm talking to my microphone. Okay, good. Merci d'être ici ce matin avec nous. Thank you for joining us this morning. I'm delighted that everything here is in 2 languages. It's makes me so happy. So welcome to our Canadian research facilities at the forefront of scientific breakthroughs panel. We are going to try here to better understand the long-term benefits of supporting fundamental research. So I'm for those that you may know me, I'm just may not know me. I'm a newcomer, so I'm Marcela Carena. I'm the new executive director of Perimeter Institute, and I'm delighted to be the moderator this morning with this leading scientists who represent some of Canada's major and most unique research facilities. So today, we will hear from them. I have been learning the past few days a lot. We will hear from them how research facilities can pursue basic research and basically ask some of the most biggest mysteries of our universe. For example, what is dark matter? We will go back to that. I hope you are curious about that. How do neutrinos behave? They are very important for the evolution of our universe. Other mysteries of the cosmos, but also how basic research is impacting deeply health and economy. So I think we're going to change the slides, which I suppose is me who does it. So I'm sorry, it's my first time, kind of. Okay, so I will introduce in some order our panelists. So I guess I will start by order there. So we are, these are our distinguished panelists, and I will start with Jody Cooley. Jody is the executive director of SNOLAB, and SNOLAB is Canada's internationally renowned underground physics lab, the deepest underground physics lab in the world. So, it's very impressive. And so, Jody is also a professor at Queen's University. And before joining Canada, we knew each other a lot from, the South, as you call it here, from the US. I'm from Argentina, so for me, the South is really the South. But, okay, I learned yesterday that you call the South the US. Good. In any case, Jody has made a brilliant career working, deciphering exactly what is dark matter. We still don't know, and it's one of the big mysteries, as I said. She was working as a member of this, what is called the Super CDMS collaboration, a big experiment based on cryogenic technologies to search for this unknown part of matter of the universe. She has been recognized with numerous prizes and awards. She has been named a fellow of the American Association for the Advancement of Science and the American Physical Society, precisely for doing groundbreaking research with the technology of, with cryogenic technology. So Jody will tell us about a Snow Lab science program and also about their most amazing training opportunities. Après, c'est Laurent. Laurent is my colleague. I'm planning to improve my French with him. That's my only hope. So Laurent is a research faculty member at the Perimeter Institute for Theoretical Physics, and he's a very distinguished mathematical physicist. He has done breakthrough contributions to the theory of quantum gravity, and in particular, important contributions addressing what we call quantum space-time entanglement. We have heard about quantum. Well, the entanglement is at the core of what we call quantum. So entanglement, quantum, put it together. Okay, so Laurent has held positions in the South, in the US, in particular in Pennsylvania State University, but also in France, in l'École Normale Supérieure. And of course, he's the recipient of many awards and prizes, too many to mention. They're not written here, no. So, important to say, he has done an amazing job in mentoring the next generation of students and postdocs. So he has done an amazing contribution to society that way. And he has been at PI since its inception, fostering curiosity-driven research and independent thinking. So I'm thrilled to be his new colleague. We move on to Chitra, so Dr. Chitra Karunakaran, I practice. So she's the Director of Science and Innovation at the Canadian Light Source. The Canadian Light Source, you can go to that webpage, it's so amazing. I mean, I was going and I was reading all the stories, it's really breathtaking, all what they can do, amazing. I was so impressed. It's home of the only synchrotron in Canada, and rightly so, one of the largest investments in science in the country. She has so she's in charge of making the Canadian Light Source be at the forefront of technological developments, and also to make it competitive with similar facilities worldwide. So this is an amazing facility that is used by, she will tell us, but is used by scientists all around the world who come here to do their research. So she is, by training, has a PhD in biosystems engineering from the University of Manitoba. And what her expertise is in agriculture innovation. So she will tell us more about that using synchrotron techniques, so beams of light for agriculture and food science research. Last but not least is Rito and Kanungo, I guess is the right way. She's a professor at St. Mary's University, which is in Halifax, correct? Yeah. I'm learning my geography, so you have to be patient with me. It took me like 25 years to learn the geography in the US, so now I'm changing. Rito is the director of Triumph, and Triumph is Canada's main accelerator laboratory. Of course, this is very close to my heart, so Triumph is a place I knew of. Both Triumph and Snow Lab are close to the science I do. I'm a theoretical physicist by training. So she's helping push the frontiers in isotope science and innovation. And isotope, when you think about PET scans, that's when you think about that, rare isotopes. So it's very important for health, of course. And she's trying to, advance, at Triumph, she's trying to advance technologies to answer very pungent questions with isotopes related to particle physics and nuclear physics, but as well we will see the impact in health. And before being in Triumph, she was in what is called IRIS. It's a facility for innovative rare isotope reaction spectroscopy in Halifax, in St. Mary's University. And she also has led leading projects in Japan and Germany, so wir können Deutsch sprechen vielleicht. And she's also a fellow of the Canadian Association of Physics and a fellow of the American Physical Society. And I just told you a tiny bit of all, so I should stop talking now. And we will start with, I think, with Ritu. She will tell us all about Triumph and Cannon's Particle Accelerator Center. Ritu, please.
So, good morning, everybody. And Marcella, will we have this? Thank you. And I also want to begin by thanking the organizers of this event for the invitation to participate. Thank you, Marcella, for the introduction. I'm Ritu Karungu, as she said, and I'm the Director of Physical Sciences at Triumph. I started in this role fairly new, just 2 months back, but I have been associated with Triumph for the last 20 years, and proud to say that Triumph is what brought me to Canada. So really a pleasure for me to introduce Triumph to you, Canada's Particle Accelerator Center, which is located in the south end of the UBC campus in beautiful Vancouver, as you see in the image there. So what are we? We are a world-renowned hub of research and innovation. And we have world-leading infrastructure. And with that, we become really a national asset. So this national asset is supported by a federal investment. And we thank the federal government for the most recent funding of close to $400 million over 5 years. So we are very proud to have built the world's largest cyclotron. And with that, we bag Canada a spot in the Guinness Book of World Records. So now we operate about 10 accelerators on site, both for fundamental science and medicine. So we are not only just doing research there, but all of this really world-class infrastructure is a great magnet to attract high-quality talent from around the world to Triumph. So we are really a hub for generating Canada's next-generation workforce through interdisciplinary training at all levels. So just to give you some idea on the scale of Triumph, so Triumph is a major multidisciplinary large-scale lab. We have about 600 in-house staff and more than 200 students and postdocs. And in addition, we have more than 1,000 visiting researchers visiting Triumph every year. So our very large international engagement in terms of partnership really speaks to our international stature. And when we say that we are a hub, more than 80% of subatomic physics research in Canada is supported by Triumph. So Triumph is involved in that. And in the process of doing all the fundamental research, we also craft ways of generating economic activity for Canada. And you see some kind of scale of $500 million over the last 5 years. Now, we are very unique in Canada. And the uniqueness really comes from the fact that we are governed by a consortium of 21 Canadian member universities stretching from coast to coast. And all of this taken together really makes us a hub in Canada for driving leading-edge research and for allowing us to position Canada as a world leader. So what do? Our research program is multifaceted. It addresses some of the most compelling challenges in contemporary science, starting from very fundamental aspects, from fundamental forces of nature to life-saving breakthroughs in health, and also helps shape some spin-off ventures. So our excellence is really in our core expertise in accelerator technology, research in isotopes, subatomic and material sciences, and related technological developments. And in the image there, you see in the blobs the very many topics of research in general that we are engaged in. So with that, then we make TRIUMPH a major asset in Canada's high-tech landscape. Let me close with that and invite all of you to visit TRIUMPH if you have not already. Thank you.
Great. I'm taking the invitation because I have been in TRIUMPH, but when I was a baby. So I would be delighted to return. Nigel, where are you? I don't know. Where are you, Nigel? Oh, you're at the back. You should be closer. He's the big boss at TRIUMPH. Are you going to invite me, Nigel? Good. Excellent. You are all witnesses. I am invited by Ritu and by Nigel. Good. So you were talking about research in isotopes, and I think that's at the core of what TRIUMPH does, because it's so unique, rare isotopes. And we know isotopes are used in medicine. So can you go a little bit more in how the activities you do in isotopes saving lives?
Yeah, thank you. That's a really great question. So TRIUMPH is one of the few places in the world where we have capacity to produce what we call rare isotopes. And these are short-lived isotopes. They are existing in our universe. They exist in nature, but they are not around naturally on Earth. And these rare isotopes, we started producing them, of course, for our fundamental research to understand the part of the universe that is not in your backyard, but you're trying to bring the universe to the lab. And in the process, therefore, of producing these rare isotopes, we are also producing the rarest drugs that lead to breakthroughs in advancing health science. And what that means is that we are producing these rare isotopes that help in cancer therapy. In particular, maybe let me just give the example of actinium-225, which is an alpha-emitting nucleus. And this alpha radiation that it is emitting, that is what is used for treating cancer. So you can really deposit that dose very locally in the cancer cells. So that's very unique compared to the other forms of radiation therapy emission. And how we produce these isotopes is with the world's largest cyclotron. We have the protons from the world's largest cyclotron. We energize them to the speed of 75%, the speed of light. And then that will go and hit a very thick and heavy target nucleus like thorium or uranium, and then it creates spallation reaction. And this spallation reaction is going to produce a whole soup of isotopes, and these are rare isotopes. And in that soup is embedded the rarest drug. So we extract that, and that's how we will deliver, breakthroughs in health science.
Thank you. I love your quote, bringing nature into the lab to study it. I think
that's what we have to do.
That's what we have to do. So that's as I said, when I usually talk about, it's not a topic for today, but we talk about antimatter. So, and then, in fact, rare isotopes, and I was mentioning PET scan, so positron emission tomography, that's what they do. They use antimatter to see where your, unfortunately, bad cells could be, and to see also how, medicine could be taking care of your cancer, actually.
And if I could just add one more sentence, how our fundamental research further helps in, let's say, health sciences or healthcare. So for our fundamental research to do our research, we really have to develop cutting-edge technology in terms of detectors, electronics, and all of this also helps translate to many other fields, including nuclear medicine in imaging. Just wanted to mention.
Yes, thank you. I think we are going to have to, I like to talk a lot, so this is my problem. Okay, so we are moving to Chitra, Dr. Karuna Karan. I love the sound of your name. So she will tell us about the Canadian light source and how researchers across Canada and around the world come there to do their science. So Chitra, please go ahead.
Good morning, everyone, and thank you, Marcella, for the introduction. So it's my pleasure to introduce the Canadian Light Source Synchrotron. As Ritu mentioned, this is another cool place in Canada. So if you haven't visited, I'm going to convince you have to visit this cool place in the cold temperatures when possible, probably in February. Canadian Light Source Synchrotron, this is a national facility, one of its kind in Canada. It's at the University of Saskatchewan campus in Saskatoon. What is this place? The synchrotron produces extremely bright infrared or X-rays that it's not possible to do in any laboratory instruments. So that's where it's a national facility in Canada and the only one in Canada. So what can we use these X-rays or infrared light? So we can look at any samples or any systems at the atomic or molecular level. So when we talk about quantum, it's all in the atomic level. So we do a lot of fundamental research in quantum and different types of materials, but it has lots of applications, especially in different areas that's important for Canada. So we do a lot of applied research as well in agriculture, environment, health, and advanced materials. So I'm going to give a snapshot of what it is in a very high level. Also, because it has applications in different areas, there are lots of industrial applications. So yes, Canadian Light Source is one of the synchrotrons in the world leading in industrial applications in these areas. So just a high level, we do hundreds of projects in these 4 different areas, but I'm going to show you few examples in different areas. So one application, you can see that there are lots of work in understanding different diseases like cancer or like neurological diseases like Alzheimer or multiple sclerosis. But what you see here is an example of like researchers from University of British Columbia, how they are using this facility to understand how certain enzymes can convert blood type A into universal blood type O. So it will address a lot of blood shortages. Also, they were able to use the facility to understand how these enzymes can also play a role in converting these type of bloods in human organ donations. So the nice thing about this research is now there is a company, AVO. It's launched as a new company, spin-off company, and they are taking this project into preclinical trials, and it's going to benefit not only Canadians, people around the world. The second one on applications in environment. Environmental applications is another signature area at the Canadian Light Source. Lots of natural resources companies or scientists use the Canadian Light Source. What you see here is an example. A company, Orano, is a uranium mining company, the biggest one in Saskatchewan. How they need this facility to understand some of the environmental systems that they deal when they extract minerals and how to manage their mine tailings to contain toxic elements. So we are doing green mining towards sustainable mining or mineral exploration. So they are like a long-term clients at the Canadian Light Source, and they are really happy we have this facility in Canada. The next one is my area, like agriculture. So this is another area the Canadian Light Source is leading in the world. Normally, the synchrotron technologies are used a lot by material scientists or physicists. And what we are leading in the world in Canada is application of this technology for providing solutions for agriculture and food. So you will see that Canada is leading in lots of food ingredients or plant-based food ingredients in the world. And so researchers from Ontario are using the synchrotron to understand how they can use corn protein as a substitute for developing meat analogs. There are lots of work on plant-based protein products, plant-based cheese, and lots of applications. And the last one I want to show is on advanced materials. We talk a lot about green energy, battery materials for electric vehicles. We all use cell phones. And this Canadian light source is important for researchers to understand at the atomic level how these materials function, but also when they have these materials put into a battery in our cell phones or electric vehicles, these intense X-rays in this facility is used by the researchers when they use these products and how they function, how we can do faster charging or longer charging batteries. So this is really critical for the research being done in Canada. So in terms of like how this facility is used by different researchers, you can see over 1,000 researchers from academia, or government labs, or industries and come and routinely use this facility. And you can see on an annual basis, more than 50 Canadian universities and colleges from 9 provinces and territories within Canada are using this facility. Also, it plays a huge role in training the next generation of talents. So more than 75% of our researchers are postdoctoral students, postdoctoral fellows or graduate students. So it plays an important role in generating the future talents in Canada.
Thank you. This is amazing. And as I said, you go to the webpage. By the way, you are also invited to the light source. I am also, so you thought this was about science, health, and economy and society, but in reality, we are doing a vacation destination tour for you. So I hope don't go in February, Saskatchewan. I was practicing that too. I am not planning to go in February, but maybe in June to visit. So you should write it down, go to your travel agent and say how that works. So we already heard quite a bit about all the impact on, so you said that on Canadian agriculture and for the world, but maybe you can say, we have to be super brief because we are absolutely out of time, but so maybe we pass directly to, thank you, Chitra, that was super good. We change from applications and real life things to applications at the end of the road, and we go to Laurent that will tell us about what theoretical physicists do.
Hello, good morning. So let me talk about Perimeter. Perimeter Institute, which has been my home for 25 years. Perimeter was founded 25 years ago in Waterloo by Mike Lazaridis from BlackBerry. And today, Perimeter Institute is, in the word of Stephen Hawking, one of the world's leading centers in theoretical physics, if not the leading center. Since then, Perimeter, which I'm going to call PI sometimes, has been supported by the government of Canada and the province of Ontario. And its mission, fundamental mission, is threefold. It's to do research, training, and outreach in theoretical physics. So let me not assume that you know what theoretical physics is, and you may wonder, what does a theoretical physicist do all day? And what is theoretical physics, and why does it matter? So let me start with the theoretical physicist. So some would say that the theoretical physicist is an explorer, someone that goes into unknown places, that it is a teacher, a mentor, someone that trains a new generation of scientific leader, that it is a team leader that lead international collaborations and scientific collaboration, or that it is an experimental designer, someone that try to propose new experiment to reveal the fundamental property of nature that we haven't really tested yet. Or that it is a philosopher, a writer, someone that just conceptualize new idea, put it in words, even invent new language, mathematical language, and English form of languages to describe the new form of nature. Or that it is a computer geek, someone that can program and analyze big data. And to some extent, a theoretical physicist is really the sum of all these things. Now, what is theoretical physics? Theoretical physics aims to understand the foundation and inner working of nature, and this from the infinitely small to the infinitely big. This is as simple as that. Now, this sharp focus leads us as a community to confront exceptionally hard problems. And when you confront exceptionally hard problems, you have to develop new concepts, new mathematical tools, new observables, new experiments, and new way to collaborate. In order to exemplify the impact of theoretical physics and how it matters, let me give you a few examples throughout history. So let's start with something that happened more than 100 years ago, one of the most major breakthroughs in theoretical physics, which was the unification of electricity and magnetism by Maxwell. One can easily say that today, most of modern technology, and in fact, most of modern economy relies on this breakthrough. Later, in the late 1980s, the discovery of the World Wide Web that leads to the invention of the internet was made by particle physicists that wanted to find new ways to collaborate and exchange data in an automated manner. And that's how the World Wide Web was invented as a byproduct of trying to do collaborative work in particle physics. More recently, let's look at the artificial intelligence boom. Maybe you don't know, but for many years, for the past 50 years, before the revolution happened, most of the funding was going, and most of the focus was going on to big computing. It turned out that this is not where the revolution came from. The revolution came from work done by theoretical physicists into what we call neural network, the property of complex systems that describes maybe the vacua of complex system, metastable vacua of complex systems like glasses, and understanding how you can tune and detune them. And so this is what really led to the artificial intelligence revolution, this fundamental work. Now, closer to home, at Perimeter, recently, we have developed a new type of software-driven astronomy. This is astronomy driven by software instead of hardware. And this leads to a radical decrease in cost, and at the same time, a radical increase in efficiency. This is a Canadian-wide collaboration called CHIME. All you have to know is C for Canadian, H is for hydrogen. And this collaboration is today the world leader in fast radio burst detection. And fast radio bursts, in case you don't know, are this blast of energy in radio frequency which are as bright as a galaxy, but we don't completely know the origin of it. Now, what do we learn from this example? We learn that perimeter drives advance in theoretical physics, but we also learn that there is some key ingredient and a simple formula that leads to transformations and discovery. First, we need vision. We need visions of the scientist that designs the project. We need visions of leaders like Mike Lazaridis. We also need visions of science policy makers that helps foundational science to exist over the long term, and this is absolutely essential. Then we need people. We need talented people. Young people, older people, people of all backgrounds, of all trainings that come together in a place where they can share, they can train, they can exchange, and they can discover. And then we need time. Theoretical physics is about the long game, not the short game. And when transformation comes, it comes with a huge reward. And so this formula, vision plus people plus time, leads to transformative discovery. And this is really what Perimeter Institute is about. Before I conclude, let me give you a few numbers. It's our anniversary. We are a relatively young institution, 25 years. And in 25 years, we have garnered more than 150 high-impact awards and honors. We have trained, something I'm very proud of, 350 postdocs, which are the highest level of training you can have in science. And they bring expertise from all around the world that they give back to us, to Canada, and to science in general. And we have trained more than 50,000 teachers during that time. Just to finish, let me give you a snapshot of Perimeter today. So we see that Perimeter is a web of different fields that are interconnected. And we create a melting pot of talent inside that share this intersection, this collaboration, and that creates really these new discoveries we're talking about, or these new ideas. Two numbers I want to emphasize is that we're today 25 full-time research faculty. We also have 21 research associates faculties, which are faculty at neighboring university, which are associated with PI, spend some time at PI. And it's necessary, this association is necessary to attract them and retain them in Canada. And just to go back a bit in time, 15 years ago, we were only a dozen faculty. So it gives you a scale of what we have achieved with so few people, and much more is to come.
Thank you, Laurent.
Thank you.
And with that, I guess Laurent and I are inviting you to our 25th anniversary. So add that in your destination chart, map. It will be a year-long celebration starting, actually the kickoff is December 12th, so right around the corner. And we will have a lot of content and a lot of events all year around. Please check on us. It will be for the general public. It will be for our academic and industry partners. And it will be for supporters of science, basic research all around the world. So going back to Laurent, so one thing, we just got 2024 Nobel Prize in Physics went to a theoretical physicist, Sean Hopfield, and Canadian scientist, Jeffrey Hinton from UToronto. So they got it for work they had done before Perimeter existed, but was basically using physics tools to develop foundational methods to understand what we call today machine learning or artificial intelligence. So Perimeter has evolved a lot, as you said. So can you tell in very short, but where are we today? What are we doing today in the area of for the AI boom direction at Perimeter?
Okay, so we have exciting news to share. That is, at Perimeter, we have a new lab called PICOL, which stands for Perimeter Quantum Intelligence Lab, which focuses on really exploring the intersection between artificial intelligence, that is machine learning, and quantum computing. And it goes both ways. So first, researchers there, what they do, they push the boundaries of machine learning to test the property of quantum matter, or even improve quantum error correcting code. And on the other hand, they use the culture of quantum computing to devise new type of AI algorithm. And what's special about this laboratory is that not only it's at the intersections of two fields, but also it mixes together pure researchers and people who are coming from the industry. In fact, researchers that in fact transit from the industry. We just have one here, Aida, that just went from postdocs to a CEO, using these tools. And so this is, in a nutshell, what PICOL is about. If I have just 1 minute, what I want to emphasize is just what's happening with PICOL is really the recipe for success for PI, is that PI always been at the forefront of creating or creating new fields or embodying new fields inside the building that were not realized either outside, like quantum information, quantum computing, quantum gravity, and working at intersection of these fields.
Thank you. Thanks a lot, Laurent. Jody, tell us about the deepest underground lab in the world.
Thank you so much to the organizers for inviting me to be on the panel. And Marcella, you're doing a great job keeping us on track.
Oh, I'm not.
I know physicists are hard to wrangle. So when I was told I could have 3 slides, I made 4.
Oh my God.
But not the PI slide. So Snow Lab is such an amazing and truly wonderful facility that we have here in Canada. And oftentimes I say y'all have in Canada because I moved to Canada here, gave up my faculty job, tenured full position as a professor at a private school in Dallas, Texas, prior to moving here to run this lab. because this lab truly is world known for the type of science that's going on and the vision that over a decade ago, visionaries like Art McDonald and David Sinclair had to build this laboratory, created an opportunity so that I could be the director of this lab someday, and I appreciate it so much. And I think it was a lot. We host at Snow Lab rare event searches and measurements. The lab itself is a class 2000 clean room that is about 5,000 square meters. That's the physical space where you can put experiments in. There's an additional 2,000 square meters of auxiliary space underground. All of this is located 2 kilometers under the earth in an active nickel mine. It's made possible through a partnership with the mining company Vale and from our visionary partners, Carleton University, the Université de Montréal, the University of Alberta, Laurentian University, and Queen's University. We are supported by the federal government through the Canadian Foundation for Innovation, CFI, and also through the province of Ontario. We have a new strategic plan out. Our strategic plan, we call it Reaching New Heights Deep Underground, and it's based on 3 pillars. Those are excellent science, cutting-edge infrastructure, and skilled people. But more importantly than that, and probably most importantly, important to Snow Lab, is our science strategy. Our strategy is to increase the understanding of the particles and forces that have shaped the universe. And from that, the majority of our research is based around 2 questions. What is the nature of the dark matter in the universe? This is 85% of the matter in the universe that's not luminous, meaning you can't see it with your eye. And the other majority of it is spent trying to understand what the nature of a tiny particle called the neutrino is. It's a fundamental building block of nature, and it's also the particle for which Art McDonald made notable discoveries for his Nobel Prize back in 2015. We also continue to collaborate in scientific research, kind of any research that requires a deep underground facility. And you might think, well, what type of things are those? So in addition to understanding the nature of the neutrino, it turns out neutrinos can be used to observe the universe itself. And so we have experiments underground that are just waiting for the next supernova explosion to happen in our galaxy, or to understand the neutrinos that are being generated by the Earth itself. We also have a program that we run with NASM University. This is a Northern Ontario School of Medicine, in understanding the effects of radiation on biological processes. So I think we all know that if you're out in space or you're taking an airplane ride a bit too often, you're being bombarded by cosmic rays, and this isn't good for you. It's why you don't want to be, next to a nuclear reactor if it melts down. It turns out that if you get too little radiation, that's also not good for your cells. And there's a whole research field around this. And the guys at NASM University, the folks at NASM University who are doing this research, are some of the leaders in the world for this type of research. We also have a small program in conjunction with Health Canada doing environmental monitoring for nuclear nonproliferation. In addition, we have started pursuing new collaborations and opportunities in emerging areas of underground science, and that includes quantum technologies. It turns out that we've actually been doing quantum sensors in our field before quantum sensors were cool. Dark matter researchers are exploring a wide range of options of what the dark matter could actually be. And some of these are really, really very light particles that when they interact in your detectors, they just produce a small amount of energy. And so it turns out that our dark matter researchers, some of them, a class of them, are actually trying to find sensors that can measure these small amounts of energies. And they're looking at materials that can better, be receptors for these interactions with very, very small particles. We also recently won a grant from the US Department of Energy to run quantum qubits underground. So we have a test facility for quantum sensors, quantum qubits. And right now, as I speak, There are a few people underground who are busily reconfiguring that facility with some electronics upgrades to put those quantum qubits underground. So that is really important in terms of our science. But in terms of our strategic plan and moving forward, the other thing I want to kind of really stress that we're doing at SNOLAB right now is in this next strategic plan that takes us through 2029, we really want to become an intellectual hub that fosters collaboration and connection. And so we have a whole host of programs that I probably won't get to talk about during this panel today, that we're working to build in order to get more people to spend more time on site, to build those connections, to build those collaborations so that people aren't just coming, putting their experiment in our lab and leaving, but they're contributing to the intellectual life of the lab. So I just want to leave you with this, and I'm not going to read through all the numbers on this slide, but I just really want to point out what an international facility this is. We have over 1,000 people in our community who are users at the laboratory. 25% of them are Canadian. These users come from 23 different countries, and they come from 165 different institutions in those countries. And so it's a truly unique facility. I would say come and see it, but unfortunately, getting a ticket to our underground lab is one of the hottest things you can do in Sudbury, and everybody wants one. We can't accommodate you all, but if you do have some kind of science or interest or experiment or something you'd like to put in our lab, come talk to us. We'd be glad to give you a tour and see what we could do. Thank you.
Thank you, Jody. So I was going to say, what about 2 kilometers underground for your next vacation destination? But it seems you will have to hold on that. I'm trying to get my good connections with Jody to see if I can make it, but I don't have, so you can't go there yet. So Jody, you talk about dark matter, as you know, is one of my fields of research. So I'm really keen on it. Jody told us dark matter, if at least today go out of those doors knowing dark matter is 85% of all the matter in the universe. You can remember that and impress your friends, your mom, your kids with that knowledge. It also, dark matter is what holds the universe together. And if you are curious about that, come to talk to me, I can explain. Or to her, of course, but I'm trying to put the theory hat here.
Yeah.
Jody, as we saw, is a leading scientist in the search for the matter. But today, now, at this moment, I want to ask you how the technology that you have developed in order to search for this very elusive and complex, and we don't know what it is, dark matter, how that can impact, for example, radiation monitoring and nuclear non-proliferation, which I think is a one-to-one very important connection. Please.
And I think my team in the audience might be thinking, how are you going to connect this one, Jody? But as a scientist, let me tell you how it works. So one of the things is, SNOLAB is a fundamental research lab. So our primary mission is to create more knowledge for which people might pick up ideas and apply it or engineer something, awesome out of it. So how do you get from dark matter to nuclear nonproliferation? So all of the experiments in our lab require really low levels of radiation in order to operate. So the experiments in our lab, for example, a banana would be radioactive to them. If you touch them with your hand, like if you touch the sensitive parts that are doing the detecting, you would be putting potassium all over the detectors and ruining them. The people who do these experiments in our lab spend an enormous amount of energy trying to find materials that have the lowest levels of uranium, thorium, and other radioactive elements in them. They will be searching for copper from certain manufacturers in a certain batch. They will be manufacturing their own copper in order to get the materials they want to be pure enough to do these experiments. So what you can imagine is in our lab, we have a whole facility dedicated to measuring radioactivity of materials. So one of these instruments is called a high purity germanium counter. The name isn't really that important, but what we do is Health Canada has a bunch of environmental monitoring stations around Canada, and they take air samples. So what happens is that then they take those samples and they'll ship them to us at Snow Lab, and we'll count them in these counters. So you can say, well, how are air samples? What are we looking for in these air samples? If you decide that you want to detonate a nuclear weapon or something like this, you're actually going to release into the atmosphere an isotope of xenon. And we can measure that isotope of xenon in these counters. So a knockoff, so the counters are there because we want to do this fundamental physics, but a knockoff effect is that they're useful for other things as well.
Thank you. So if you are planning any nuclear activity, be aware because she will catch you. Okay, so we move on. We are kind of late, so I will ask you that you are concise, please, in the answers. But I will start from that end now. So we have said and we have heard during these conversations the past 2 days how important is training in STEM. And of course, these facilities are leading training in STEM in many ways. So all your facilities are unique. And so I have two parts of the question, and I will maybe not go over everybody for all the questions. But so you, basically, first of all, as unique facilities, you are main attractors for top and very diverse talent. And so then you are doing this particular training. So I would like that you tell me a bit, maybe about how are the main ways that you do training. So that's part number one. So let's go maybe a bit around with some, just one program that you love. So pick one, one program that you love.
So that means I get to pick two, right?
No.
Okay. All right. So,
Johnny, please.
All right. So I'm going to step aside what everybody does, which is undergraduates, graduate training, things like that, and talk about our engineering training program. We actually take into our lab and train students who recently got their engineering degree, and we partner them on different projects in the lab, rotate them around so that they can get certified by, get their PEO certification. So this is their professional engineering certification in the province of Ontario. And this has been a really successful program and one I'm really proud of.
Thank you. I'm bouncing back. Ritu, what do you think about your preferred training program?
So at Triumph, we have, as I said, quite a multidisciplinary research program, and that therefore also brings for our students and postdocs an environment where they can master multiple kinds of skill set. And we do this through, of course, the hands-on work. And that's absolutely the major important thing that they get, the hands-on work. But together with that, they are also able to do like interdisciplinary, more connected workshops, etc. There's another important aspect at Triumph, which is the connection with Triumph Innovations. Mm-hmm. And the connection with Triumph Innovations then also allows them the avenue to connect to applied aspects of their fundamental work. And that's how we build their skills of translating fundamental science to applications and in industry. So we have a lot of spin-off companies from Triumph, and we connect some of our trainees to the spin-off companies.
Thank you. So the I guess what I hear is the hands-on is the crucial part here. Maybe Chitrak, you want to share like your preferred program or for training?
Like any other national facility, Canadian Light Source also play a big role on training undergraduate, graduate, and postdoctoral fellows. That's a big part of the training program. But we do have a targeted training program called Educational Outreach Program. The main goal is to reach to students at the high school age to increase their awareness of these scientific programs. And so this is a program that's well done. And so the way it is done is we would bring teachers through their professional development program. Then the teachers know these programs at the Canadian Light Source, where they will bring high school students who are a part of like science clubs. And it has a huge impact. For example, yesterday, one of the professors from McGill University, she has a graduate student, and she was going to write a letter for her scholarship, and the student said she benefited from one of these high school programs. She came and used the Canadian light source that made her go into science in her higher studies.
And here, I guess we are, and maybe we can divide this in two parts. So one is the STEM training, and I think, and the other one is, of course, the outreach to students. So I will go back to you a bit in a second, but maybe I let Laurent tell us a little bit about our PSI program. That's one that is dear to my heart.
The PSI program. I mean, my favorite program, if I may, for me is the postdoctoral program we have at PI. So postdoc, someone with already has a PhD, maybe one postdoc, and they come to PI to go from being a good scientist to future leader in science. And I think we are one of the leading institutions in the world for that. Just to give you an example, this is the moment we select them. So we just have right now like 1,500 applicants, and we have 15 positions, right? So it's ultra selective to get in. On the other hand, we're also competing for the best of these postdocs with institutions like Harvard and Princeton. So it's also super competitive for us to compete. And the way we attract them is because at PI, the unique thing is that if you're a postdoctoral researcher at PI, you become your own independent researcher. So my mentoring is not to tell them what to do, but to accompany them along or push them or encourage them. And when I say me, it's any faculty at PI to become future leader of science, often creating new fields of science. And so what very attractive to them is this interdisciplinary. There's no other theoretical physics institute in the world where you can jump from quantum gravity to quantum information to quantum AI as in the same coffee table.
So actually, I have to say that when I am asked, about me coming here, one of the things I say a bit as a joke, but in reality is very much true. The first times I heard of perimeter was when my institution in the US, Fermi, the biggest particle physics lab in the US, and the University of Chicago started competing with PI for these postdoctoral fellows. And I'm proud now to say that Fermilab sometimes won, many times PI won. So PI is bringing to Canada the brightest minds from around the world, and we train them further. So I totally agree. There is also a very interesting program for, maybe you can say a few words, because I'm really proud of what PI is doing.
So we also have on the other end of the spectrum a master program called PSI program, which brings students from all over the country. I'm here in 23, maybe it's like 30 different countries. And we have parity in this program. Half of the students are men, half the women are women. And we take complete care of them and put them under intense, very, very, very intense and unique 1 year fully inclusive theoretical physics boost. And then they go all over the place. We keep some of them, but then they create a new form of alumni and connection and very, very strong collaboration across different disciplines, which I think will affect science in the long term, because these people trust each other, they know each other, and they end up in very different fields. So I think this will have in the long run a huge impact.
And then this, I would say EDI component, if you want, this is an amazing program, because nowhere in the world you have a program at the master level where it's 50-50. So this is really impressive. So changing a little bit gears because of time, here Emily is my clock and she's looking at me seriously. So it is still related, but Jody, maybe I ask you this question. So of course, a significant amount of the people we train with all our heart go out of academics, rightly so, and go into industry and into the private sector in many ways. So I'm interested in knowing two things, basically. First, in which areas, so your mostly highly qualified personnel advance, in which areas of society and the private sector they advance? And second, what do you think are the main skills that we all here, but please you answer, we are providing them, that are the skills that make them so desirable and so successful once they are outside of academia?
Yeah, so in 2022, Snow Lab commissioned a study. TD Banks did it. I see Daniel Banks sitting right here, did it for us, of our alumni. And what we found, or what we were told that Daniel's team found, was that our HQP alumni are strongly represented not only in academia, but also in professional services. So this would be like startups, engineering, consulting, scientific research and development. So like national labs or the Defense Council. Also software and commerce, so places like Amazon and Google, and manufacturing, ICT devices, aerospace, and public administration. So especially looking at Health Canada as being some of the employers. In that study, we also asked them to identify the skills that they thought were most important. And I'm sorry, I'm reading off my notes, but I want to, because we actually did a study, I want it to be the information I'm giving most accurate. But those skills that they identified were technical skills and advanced coding simulations, data science, statistics, machine learning, experiment design and planning. So they also, in addition to sort of those hard skills, they identified softer or the professional skills. Effective oral and written communication, time management, the ability to work in teams, understanding the societal and large scientific organizations, and interdisciplinary perspectives. And so all of those are skills that people who were trained at Snow Lab identified as being really important to them as they transitioned to industry and different roles in industry. So that's what I can tell you from the Snow Lab perspective.
Thank you. And I think we are like 10 minutes or so. So before, I have many more questions for you. So I will corner you in the coffee break.